Welcome, ladies and gentlemen. Let's go ahead and take a look at our related rates problem for Bellwork. And so we have a strategy that will help us tackle these kinds of problems. After reading the problem carefully, we want to write down our known rate and write down the rate that we're trying to find, and that'll help provide our focus for the rest of the problem. So a fish is reeled in at a rate of 1 foot per second from a bridge 15 feet above the water. At what rate is the angle between the line and the water changing when there is 25 feet of line out? And so what I tried to do was show that I intended the fishing rod, the tip of the rod, to stay a constant 15 feet above the water level. So I'm going to go ahead and let that be fixed when I go and set up the problem. All right, so after reading it carefully, we want to go ahead and label our picture with appropriate quantities and then write down our known rates and the rate that we're trying to find in Lmx notation. So let's go ahead and take a look. We can transfer our angle, right? Our angle between the line and the water we'll call theta. And we're calling the length of line x. That looks like the hypotenuse in this right triangle. So we can call that x. And the constant, the only constant that we can label in our picture is the height above the water level. The same constant at 15 feet, so we can go ahead and label that. Yes? Awesome. Let's go ahead and share our known rate then with Lmx notation. So what did you have for your known rate here? Kobe?
Dx dt equals 1.
Awesome. So our known rate is dx dt equals negative 1 foot per second. And that makes sense because you're reeling in the line as you pull in the fish towards the dock, right? And so that length x should be decreasing, and that explains the negative in my rate of change. Great. So raise your hand if you have dx dt equals negative 1 feet per second. Great. Next up, my rate that I'm trying to find. So what are we trying to find? Go ahead and tell the class when I call on you. Sydney, don't get down on yourself. I believe in you. So what are we trying to find, Courtney?
d theta dt.
D theta dt. Good. So we're trying to find d theta dt. And do we have a moment in time, an instant, right? D theta dt when? Are we given anything else, Riley?
Yeah, when x equals 25.
So when the line out, that would be hypotenuse length still, that would be x equals 25. Awesome. Now we want to make sure that we're not plugging in that moment in time data until the very end after we've isolated our known rate. That way, our unknown rate, that way we won't run the risk of losing variable quantities that in fact change throughout the problem. And that's why I hold off on my moment in time data until the very end. And I would encourage you to do the same. All right, so now our job is to come up with a relationship, an equation that involves the quantities of my rates. And so we have our known rate is dx dt, our unknown rate is d theta dt. We need an equation that relates x and theta. What equation did you use? Sophia? Sine. Raise your hand if you use sine. Did you use sine? Everybody use sine. Hey, nice. So in that case, right, we want to use sine. We could have used any of the 6, but we have the constant 15, and we have the x and the theta, so that's opposite over hypotenuse. I'm going with sine as well. So the sine of theta equals opposite 15 over hypotenuse x. Awesome. And now that we've generated a relationship between the quantities that are in my rates, I'm ready to differentiate both sides with respect to time. So we'll go ahead and differentiate both sides with respect to time. And the derivative of sine of theta with respect to time is sine goes to cosine of theta, the derivative of the trig function with the angle, then times the derivative of the angle. And there's where my d theta dt comes from. Good. On the right-hand side, the derivative with respect to time of 15 over x, again, chain rule, right? We're not differentiating a t function, we're differentiating an x function, right, with respect to time. So here we go. The derivative of 15 over x looks like opposite of 15 over x squared. I'm doing the power rule where the current exponent on x is negative 1, differentiates to negative 1 times x to the negative 2 with the constant multiplier 15, then times the derivative of the base. The derivative of the base with respect to time is my dx dt. Raise your hand if you have the correct differentiation. Differentiation in red. Yes? Yes! And what do we want? We want d theta dt. So we'll go ahead and solve for that. We can do that in one step. Looks like my d theta dt will be given by negative 15 dx dt. I can keep all that on top. And I can write a single fraction when I divide over, go gadget arm. It looks like we've got the x squared down there. And we've got the cosine theta. Is that right? Did I get everybody? Awesome. Now and only then will we go ahead and evaluate this for my x equals 25 and see what we can generate. So my d theta dt is going to be given by negative 15 times dx dt times x squared times cosine theta. Wow, we've got a lot of things there, Mr. Fritz. So let's see. dx dt was negative 1. At the instant when there's 25 feet of line out, so that's 25 for x, quantity squared, and that missing information here, right, is my cosine of theta. And for that moment in time information, we've got to go back to the picture. At the instant when x equals 25, it looks to me like we have a Pythagorean triple, don't we? We have a scalar multiple of a Pythagorean triple. If this is 15 fixed, if this is the moment in time when x is 25 feet, then it looks like a 3, 4, 5, so 20 feet. And you can do that with Pythagorean theorem or whatever, right? But I'm going to use 20 for the adjacent side length. Now it'll be easy for me to pick out my cosine ratio. The cosine ratio in a reference to this acute angle would be adjacent over hypotenuse, and 20 over 25 reduces nicely to 4/5. However, I see that 25 right there. So I'll leave it as 20 over 25, and I'll cancel one of those 25s out. Of course, at any time, we can certainly go to our calculator and math bracket at the end, right? And so it looks to me like we got the negative times the negative is a positive, and I got 0.03 when I did this yesterday, radians per second. So I got 0.03, and that was exact, wasn't it? There was no more decimals, there was no rounding, right? It was 0.03 radians per second, and that's exact. Awesome. Raise your hand if you generated that same as well. Awesome. So positive, right? Because it looks to me like the magnitude of theta would be increasing as the fish is getting closer to the dock, right? Awesome. What questions do you guys have about our Bellwork today? Okay. I'm going to go ahead and pause the recording. We'll take care of our OTL number 5 check. All right, so today we've got a warm-up that's going to set the stage for a technique known as linearization, okay? We already have all the tools we need to generate a linearization for a function. All those tools lie in our tangent line equation, right? So let's write the equation of the line tangent to the curve at x equals 2. If we're given a function f of x equals the square root of x minus 1, and we're doing this non-calculator right now. So go ahead and generate that equation non-calculator. You may do so with your partner. Please be ready to share. Okay, so to write the equation of a tangent line, we need the same 3 things. We need the x coordinate of the point of tangency, the y coordinate of the point of tangency, and yes, that's right, the slope of the tangent line. And then where do we go for that? We'll go to our derivative. And so what did you get for your expression for f prime of x with x's in it? What did you get for your f prime of x function? Brendan?
1 over 2 times the square root of x.
Awesome, thank you. So I get 1 over 2 times the square root of x minus 1 as well. I can now evaluate that at my x value of concern at x equals 2, and that'll give me the slope of the tangent line that I need to complete the process. So it looks to me like evaluated, we get 1 over 2 times the square root of 2 minus 1. So I get 2 minus 1 is 1, square root of 1 is 1, 1/2, 1/2. Raise your hand if you had 1/2 for the slope of the tangent. 1/2? Awesome. So do I. This completes the puzzle. So we've got our x sub 1 is 2. Our y value is given by my original function f evaluated at x equals 2. 2 minus 1 is 1, square root of 1 is 1. So I've got to write an equation of the tangent line with x coordinate of the point of tangency 2, y coordinate of the point of tangency 1, and slope of the tangent line 1/2. Hey, I can do that. I'll go ahead and start out with my point slope form. Y minus y sub 1 equals m times the quantity x minus x. All right, let's go ahead and rewrite that. So y minus equals, and we've got them all. We've got y minus 1 equals 1/2 times quantity x minus 2. That's a funny looking 2, Mr. Fritz. Thank you. And depending upon the directions, we could leave our final answer in point slope form, right? But I'm going to go ahead and add over that one because this is the form we'll use for a linearization. But first, raise your hand if you had the equivalent. Either of these lines is fine. Or you could just read through. Good job, you guys. Awesome. So a linearization is just a tangent line to a given function at a particular place, like the warm-up. So let's start with our point slope form, solve it for y, and then we'll rename it L of x to show that we're using a linearization for a given function x. So point slope form with letters is y minus y sub 1 equals slope n times the quantity x minus x sub 1. If we were to solve this for y, right, we could do so in one step simply by adding over the y sub 1. We'll leave this as quantity x minus x sub 1 in parentheses. So y equals m times quantity x minus x sub 1 plus y sub 1. We're going to go ahead and rename this L of x, and we're also going to rename our y sub 1 the value of my original function. That's where I went to get y sub 1. I plugged in 2 to f of x to generate the y coordinate of my point of tangency. And my slope, we went to f prime and evaluated it at my x value concern, so we'll also call that f prime. And now we'll rename our linearization. So I'm going to call this L of x. Where did we go to get m? We evaluated f prime at my x value concern. I'll call it a. X is still our independent variable that changes, minus, but our x coordinate we'll call a. And to generate our y value, we evaluate our original function at the x value concern, still a. So the y coordinate would be f of a. Put it all together, and we have a formula generalized for L of x, the linearization of a function. A linearization is just using a tangent line, right, at a particular place to approximate function values. Why might we use a tangent line to approximate function values? Well, a line is very easy to work with, right? We know all there is to know about lines, whereas a function might be more complicated. In fact, linearization and derivatives were used to approximate, right, all kinds of complicated functions, not the least of which are square roots or cube roots, long before calculators existed. When we deal with series and Taylor polynomials in second semester, right, we're actually just going to use derivatives to approximate complicated functions. And it turns out that second, third, fourth order Taylor polynomials can be very, very, very close to the actual function values, even though they just use the function's first, second, and third derivatives to make an approximation for the original function. And we know a lot about derivatives. All right, let's go ahead and see what kinds of things you might be asking. So let's find the linearization of a given function at a particular x value. We'll approximate sine of 3.25 without a calculator, and then we'll use the calculator to determine the accuracy of our approximation. All right, so let's go ahead and see if we can do the same thing we just did, but now with a new name, right? Same stuff, but different packaging. L of x is the equation of a tangent line. So we're going to need the same things, right? We're still going to need our x coordinate of the point of tangency. We're going to need our y coordinate of the point of tangency, and now we're calling that, right? We're calling that f at a. And we need our slope of the tangent line. Bless you. We'll call that f prime at a.
Bless you.
All right. What's our a value here? Well, we're going to generate this linearization at x equals pi. So our y coordinate of the point of tangency is going to be f at pi, and the slope of the tangent line will be given by f prime of pi. Let's do it. So given an original function, f of x equals sine of x, f prime of x is given by, and what do we get for that? Grace?
Cosine pi.
Cosine of x. Awesome. And then we'll evaluate it at x equals pi. So I get cosine of pi is -1. You need -1? Yeah? All right. We're ready for our L of x. So L of x is given by f prime at a times quantity x minus a plus f at a. For us, bless you. Right? Our L of x will be given by f prime at pi is -1 times quantity x minus pi plus f at pi, and we still need that. So what's f at pi? That's my original function evaluated at pi, and sine of pi is 0. All right, so we have 0. Great. So L of x is given by -1 times x minus pi plus 0. Can we approximate the sine of 3.25 without a calculator? Yeah, we can do that exactly without a calculator by evaluating my function, my linearization function, L of x, when x equals 3.25. Right? So we'll simply plug that in. Let's see how close we get. So I get -1 times 3.25 minus pi. And that equals -3.25 plus pi. We've done this exactly in algebraic. Why? Because we're going to compare it with the actual value of sine, well, with the calculator's approximation for sine of 3.25 and see how well we did. All right? Guys ready? Let's do it. Go to my emulator. I want to make sure we're in the right mode here. Okay, so I've got ratios up. Great. So we're going to go ahead and generate the sine of 3.25 and the calculator's approximation, which is giving us -0.108195135, and our linearization, which just uses a line to approximate that curved sine function, -3.25 plus pi, and we're getting, oh my goodness, -1.08406. So that's not too shabby, right? So let's go ahead and copy some of this. So this is about, oh boy, that just won't do. This is about -0.108,407. And now's a good time for ... And now let's versus. The calculator was -0.108,195. ... Now we're going to go ahead and compare the difference. Okay, so what are we going to do? Well, I'm going to take this and subtract my sine of 3.25 to compare and see how well we did. By golly, 0.0002122, so that's pretty good. So the difference between those is within 0.0002122. Hey, that's pretty good. Okay, what's going to happen to this linearization and its accuracy as we move farther away from x equals pi? Well, clearly, right, the line is going to diverge from the curved portion of my sine vector. And so linearization does a good job of approximating. In fact, this was a really good job. All right, we moved over a full tenth plus, and yet we were still within 0.0002, bless you, units of the calculator's approximation. So linearization does a great job so long as you're close to the point of tangency, but as you move farther away, that'll diverge, right? We saw that before. What else can we be asked to do? Well, let's go ahead and see how we approximated square roots or cube roots and radicals prior to calculator technology. In fact, we did that with derivatives. In fact, historically, it was the other way around. We would use calculus to approximate these values, right, before we had the prevalence of calculators and technology. So let's go ahead and use linearization to approximate the following numbers, and let's see how close we get. All right, so let's approximate the square root of 66. First thing we need to do is pick a function, all right, that we can use to approximate that. And so which function would be good? Well, I think the square root function, right, would be the function to use. And now we need to pick a place where we're going to generate that linearization. So we need to write an equation of tangent line at a particular place on my function. So let's use f of x equals square root of x. Let's do the linearization at x equals, well, is there a convenient x value nearby that we know? What? 64. If we generate our linearization surrounding x equals 64, then we have an exact value that would be convenient to do non-calculator and compare that with the calculator. All right, let's do it. So what do we need? We need the same three things, right? So x equals a, x equals 64. F at a is my y coordinate, so I plug in 64 to my function. F of 64 is the square root of 64, and that's 8. And then we need our f prime at a. Our f prime at a is the value of my derivative. Well, Brendan told us before that if f of x is given by a square root, then f prime of x is given by 1 over 2 times the square root. We've done that a lot. Therefore, my f prime at a would be 1 over 2 times the square root of 64. 1 over 2 times 8, and that's 1/16. Now, did I do that right? Square root of 64 is 8 times 2 is 16 at the bottom. Everybody good? Great. So we're all ready for our L of x. We know that our L of x linearization is given by f prime at a times quantity x minus a plus f at a. That's just the equation of a tangent line with a new name. Our particular linearization would be L of x equals dun 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 1/16 times quantity x minus 64 plus 8. Yes? All right, so let's do it. Do what? We're trying to use a line, a linearization, right, to approximate a square root of 66 for all things, right? Well, this is great. This is way easier to approximate this. So let's go ahead and plug in what? 66. If I plug in 66 into my linearization, I can see what my line approximates and then compare it with the calculator. So let's do it. L of 66 equals 1/16 times 2. I better do that. Looks like plug in 2 first. Better do one more line, Tyler. One more line. All right. So I'll just keep going left to right now because we're running out of board. 66 minus 64 is 2. So I'm getting 1/8 plus 8. So as an approximation, I'm getting 8.125. Yeah, 8 and 8 is 1.25. 8.125 for my estimate versus, see how we did. Dun, 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 dun. Oh, sorry. Sorry about that. Pretty good. I think it's pretty good. Well, I'm going to use a different color though. Versus 8.1240388. All right, so let's go ahead and compare. I'm going to subtract off my 8.125. Hey, we didn't even, nope, we didn't do as well as last time, but pretty well. So this is only 1, 2, 3, 9, 6, Can I get an exclamation point? Huzzah! That's pretty sweet. Okay, one more, and then we'll take a look at our final application in Unit 3. Firstly, what function would be appropriate to approximate the cube root of 66 using lines? Well, how about the cube root function? F of x is given by the cube root of x, and we also need a place. And so what makes sense, right, to center my approximation around something that I can evaluate now in calculator easily? Are there any perfect cubes around? What? 64. We'll use 64 again, right? But this time for a very different reason. We're not selecting 64 because it's 8 squared. We're selecting 64 because it's 4 cubed, right? So we'll still do an at, and we'll do x equals 64. So I've got x equals 64. My f at 64, or f at a is f at 64, and that is 4 this time. And my f prime at a, my slope of the tangent, that would be f prime at 64, and so for that I need my first derivative. So this is a different derivative rule. I'll still use power rule. So f prime of x is given by exponent times the base raised to 1 less. So it's 1 less than 1/3? Negative 2/3, right? So I'll go ahead and evaluate 1 over 3 cube root of x. And I'm thinking if I do it like this, I'm getting cube root of x squared. If I do the cube root of x squared, it'll be easier for me to do non-calculator because that's what we're doing. We're trying to approximate something, right? Exact the cube root of 66 without a calculator. Let's see how well we do. So let's evaluate this at 64. So I'm getting, oh boy, 1 over 3 times, and what is the cube root of 64? Well, that's 4 squared is 16. So I'm getting 1 over 3/16, which is 148. Is that right? 148? And now I've got our final piece of the puzzle. All right, let's do it. So L of x. And this time we're going to jump right to the equation because you guys have now seen the form multiple times. F prime at a is 148 times quantity x minus 64. Plus 4. And we want L of 66 equals 148 times 66 minus 64 plus 4. So that's 2/48. And I was doing great with my decimals until I got to 124. But I sure know that as a mixed number. 124. Oh, you didn't. Yeah, I did. Versus, moment of truth. Dun, 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 dun. So my 4 and 124th is 4.0416 repeating. My calculator gives me an approximation for the cube root, math 4, cube root of 66 as, oh, that's pretty good. Muscle mass focus there. So I'm going to go ahead and subtract and see how we did. Can I grab it? Can I grab that? Yeah? That was fun. So the calculator approximated 4.04124. So that's within, my favorite part, that's within 0.00426665. Hey, not too shabby. Exclamation point? I think so. I think we deserve one on this Tuesday, Friday. Cool. So what questions do you guys have about our linearization? Using a tangent line to approximate a function, right, is a lot easier if you don't have the calculator. Sydney.
Every time we do this, we need to go like 8 decimals out for that whole thing.
I just
Is like 3 good or
No,
no?
you should do,
Like 4.
yeah, you should show here so you can see how close it is. Yeah,
So 4.
because if you only went 3, we wouldn't,
Really
we
dumb.
wouldn't gain anything, but we want to know. But yeah, that's fine. We want to see how good of a job we're doing. All right, guys. We got a printable for you guys, and now let's switch gears to differentials, which are actually connected directly to our linearization. Why? Because a differential uses the instantaneous rate of change, namely the slope of the tangent to the curve, right, to make an approximation for the change in the y values experienced for a little step. Call it dx as opposed to delta x. And so I changed this from the printable this morning because it made sense to me to start with the original function y equals f of x. In Leibniz notation, recall that we could take the derivative of both sides and we generate dy dx, the derivative of y with respect to x, would be given by f prime of x. Now, while Leibniz considered this as a quotient, right, dy dx, if we were to think about this dy and dx as separate entities, right, if we were to think about this dy as representing a very small change in y, an infinitesimal, Leibniz called it, and this dx is a very small change in x, right, a very small step, delta x, in my x values, then we could break this up and get an anticipated change in my y value using the instantaneous rate of change, that is the first derivative at my point of concern x, multiplied by that small step. And so the differential dy is given by f prime of x times dx, where I'm considering dy and dx as differentials, as their own separate entities. Dy, my anticipated change in my y value, right, still uses a line, the instantaneous rate of change at a particular x value. It still uses the slope of the tangent, then just multiplied by some small step dx over to get an anticipated change in my function values. Call it dy. So what does dx represent? Dx represents a very small change in x. It's a differential. dy represents a very small change in y. In fact, it's my anticipated change in the y values of my function using a line. You guessed it. The approximation, right, the anticipated change in y dy is going to be more close to the true change in y if, as long as I do a small step, right? The smaller my step away from my point of tangency, the better my approximation anticipated change is going to be to the true value. Let's go ahead and try it out. So let's find a formula for dy, that is the differential, the anticipated small change in y. If my original function y equals f of x is given by 3x squared minus 5x. Well, in terms of my differential, that's easy. I can anticipate dy by taking f prime of x and multiplying by dx. dy is my dependent variable. It depends on f prime of x and dx, the independent variables. So let's go ahead and see what happens. I can get there by differentiating both sides. My f prime of x would be 6x minus 5. I'm going to go ahead and put that in parentheses to show my f prime of x, and then times dx. This formula will give me a way to anticipate, right, a change in y based on some small step dx. If I were to use this differential to approximate the change in y, starting at the point of tangency x equals 1, and stepping over 0.08, right, I could get an approximation for the new function value. I could get the anticipated change in my y value, call it the differential dy. How would I get that? Easy. I'll evaluate my dy formula. So I anticipate the change in y based on the instantaneous rate of change at x equals 1 to be given by 6 times 1 minus 5 times dx, the anticipated change. I'll simply put in 1 for the x value. Very good? So I do 6 times 1 is 6, minus 5 is 1, times 0.08. So it looks to me like if I stepped over from x equals 1 on my parabola, 3x squared minus 5x, if I stepped over 0.08 x units, I anticipate my y units to also change by 0.08. Now is that going to be the same no matter where I look? No, my value of f prime is going to be different depending upon where I'm drawing my linearization, my point of tangency from, right? And so differentials allow me a way to anticipate change in function values based on small change in x values. All right, let's close it up, and then we're going to go ahead and take a look at some AP changes coming fresh this year. So the linearization L of x of a given function f at x equals a is given by, dun dun dun. And if y equals f of x, then the differential dy is given by, fill in the blank, and then be ready to share. Okay, with F's and A's and L's, what does my formula L of x look like in generalized form? Tyler?
L of x equals f prime divided times x minus a plus
Excellent. Raise your hand if you have the same as Tyler. Great work. The differential dy is given by, if y equals f of x, then dy equals, Danny? That's it. And raise your hand if you have the same as Danny. You guys just killed it. I'm going to go ahead and box this bad boy because I want PDFable. And 1, 2. And we're very close to our Thanksgiving shortened assignment. It looks like 1, 3, 5, 15, 17, 19, 27, 28 for a total of 8, but you'll notice they're all odds, so you have the opportunity to check these bad boys in the back. And you can jot them down in your note sheet so you have them. I didn't have an even number of printouts, so I'll have to write these down. We've already talked about our review day, Tuesday, November 29th. When you come back, we're going to take a look at some AP practice questions for the free response portion of the exam, and then have some structured review time leading up to your Unit 3 test, applications of derivatives, on Thursday, the 1st of December. On Tuesday, I'll have a concept and skill guide for you, just like always, so you can take a look at the kinds of topics, concepts, and skills to be assessed on a Thursday exam. The final thing I'd like to share is new changes, and I got this directly off of AP Central. You'll notice that the exam format for the 2016-17 AP Calculus classes, both AB and BC, has changed slightly. Last year, the multiple choice was the 28 and 17, right, was the split for Part A, non-calculator, versus Part B, calculator allowed. Well, based on feedback from educators around the country, they actually changed the split between the non-calculator and calculator allowed. So it's still 45 questions and 50% of your exam score, right? But now there's 30 non-calculator questions for 60 minutes, and then 15 graphing calculator required questions. So that's maybe a minor change for you, maybe not such a minor change. The free response remains the same, still half your score. Now, 2 questions, right, are the first ones that you get that the graphing calculator required, and then 4 questions are the non-calculator. That's no change from last year. So you remember that from last year, we could continue working on those first ones, but you could have to put the calculator away and so on and so forth. So we'll take a look at some practice AP problems then on Tuesday the 29th, the Thanksgiving holiday. The rest of the time will be yours to work quietly, and I'll upload the recording.